she got her bachelor's degree in chemical physics from the University of Edinburgh and PhD in chemistry from the University of Edinburgh in 1986. And she did her habilitation in experimental physics from Freiburg University in Germany. And currently, she is the chair of chemistry in the School of Chemistry at the University of Edinburgh since 2013. Previously, she was head of school in School of Chemistry in the University of Edinburgh and chair of atomic and molecular physics in the Department of Physics, Campbell특강 University in Sweden. And also, she was on the department head in Max Born Institute in Berlin, Germany, and also a professor at the physics department in Freiburg University, Germany. She got so many awards and prizes. I just name a few. She got awards from the German Research Foundation and the Royal British Academy of Science and British Research Council. And she's elected member of Royal Society for the Arts and Sciences in Gothenburg. And he is elected as a full member of the Royal Society, Royal British Academy of Science, and President Fellow of the Royal Society of Edinburgh, and Fellow of the Royal Society of Chemistry, and Fellow of the Institute of Physics, and Fellow of the Royal Society of London. That all of it is a very great honor. And he was the president of the Faraday Division of the Royal Society of Chemistry from 2015 to 18, and she got other awards as well. And she served as numerous members in national and international assignments, and for example, research committee member and review panel and supervisory board and so forth. And she supervised more than 30 PhD students and more than 15 postdocs. And she gave over 300 invited talks. And her citations are over 14,000. You know what that means. So please welcome our speaker, Professor Campbell.
Okay, thank you very much. It's quite scary to hear that all read out. Shows how old I am, if nothing else. It's a very great pleasure for me to be here, and a particular pleasure to now add the EY University logo to my affiliation. So I will be coming back here on a regular basis, and I hope to meet lots of you over that time and talk to you. So I thought I would, rather than going into lots of detail of recent research that I'm doing, I thought I would tell you a little bit about my journey and what I've done through the years and why I did things and what happened to me. And maybe give you some words of advice at the end, as an old grey-haired professor should do. First of all, we have a nice exchange program between Edinburgh and EY, which is really just getting going after the pandemic. So we have had 2 students visiting here in the past year, and we will have another 2 coming in a couple of weeks' time. So I thought I would just remind you about that. This work. So it's really between chemistry, nanoscience, and physics, also chemical engineering and material science, and chemistry at Edinburgh. So it's a rather complicated agreement that we have, and other things are possible. So I think in principle, it's possible for master's students to be exchanged. So if we can develop some nice collaborations between groups in the 2 universities, there's possibility for people to come in either direction for a few months. At the moment, it's undergraduate students, or in our case, our students do an integrated master's program. So, okay, why would you want to come to Edinburgh? I have to say how great Edinburgh is. EY is also great, so it's nice to have both under my name. But Edinburgh is now 15th in the QS rankings, which is fairly good. It's the top university in Scotland, 6th oldest in the UK, a good number of students. And traditionally, it's always been supportive of female students. So some of the first female graduates in the United Kingdom came from Edinburgh University. Just point out here, Scotland, I'm saying it's the top university in Scotland. Scotland only has a total population of 5 million, which I think is half the population of Seoul. So that maybe puts it in perspective a little bit. But it's a beautiful place. Some of you have been there. Would like to see many more coming. It's a very beautiful city, quite a small city, 500,000 people, which is a tiny village compared to where we are now. But it means you can easily walk around the city and see lots of different things. Interesting natives and nice nature very, very close by. So it's very easy to get to the seaside, to get to the mountains. Scotland is very small, so you can easily explore the countryside. And this is a group that came to us in 2019. So in time just before everything shut down around the world, we had a very nice few days in Edinburgh, and I'm sure you recognize some of the faces there. And we hope that we're going to have more of these opportunities in the future. Good Korean connections in Edinburgh. If you do come to Edinburgh for a longer period, you shouldn't feel homesick. There are lots of very good Korean restaurants very close to the university. There's now a Scottish Centre for Korean Studies that organises cultural events throughout the year. And we have our long tradition. So here are 3 well-known Korean alumni of the university. So a nice connection there. And I personally think there are quite close similarities between Korea and Scotland. I think we're quite similar in many ways. So these are the exchanges. Our students come in the last year of a 5-year integrated master's degree and do a full-time research project. So I'm always looking out for good groups to send the students to. And I'm very grateful to people who host them. The EY University students at the moment would be undergraduates who would come to Edinburgh for 1 or 2 semesters and take a mixture of lecture courses, typically 3 courses per semester. But one of these courses can be a research project. So it's possible to work in a research group with part of that. And it's possible to take courses. The research project can be in physics or it could be in engineering, as long as I know in advance and I can talk to the people there. And at least one of the courses can be taken in quite a different subject area if that fits in with the EY curriculum, and you can get credit for that. So the nice thing about the Scottish education system is that it's very flexible. And in the first 2 years, students can take very, very different mixes of courses. They're not focused in on their chemistry or physics. And here I've just put down some of the projects or some of the groups in chemistry that would give interesting projects to work on. So everything from rather physicsy stuff in the chemical physics side to medicinal chemistry, almost biology, and quite a lot of sustainable chemistry work is going on. So there are lots of interesting possibilities. Okay, but that was just a little bit of advertising. That's not really what I'm supposed to talk about. So my journey in science. My journey started here. So this is a small island on the west coast of Scotland called the island of Bute. So this is where I was born. These are the pictures here. This was almost the view from the house that I grew up in on the island. So very nice mountains and water. And there's no connection to the mainland by bridge. So the only connection is a little ferry that goes many times a day. So I was born approximately here in the small hospital on the island. And I grew up on the island. I went to school here. So I left when I was 18 years old to go to university in Edinburgh. And there, as you heard in the introduction, I did a BSc in chemical physics, which gave me a nice mixture of basic chemistry, mainly physical chemistry, and physics, quantum physics, solid state physics, materials chemistry. So it was a very nice mix of courses. And we're still running this degree, and I'm now responsible for developing that, which is a lot of fun for me to do. And then I stayed to do a PhD. I was very interested in questions like, what happens to molecules when they collide? How do chemical reactions take place? What do the atoms do? How does it happen? So I was much more interested in these fundamental kind of physicsy questions about how to understand chemistry, rather than standing in a lab and mixing liquids together with strong smells. I never really liked that. So I got my PhD in 1985. And then I moved to Germany to do a postdoc position for a couple of years. And there I started out doing experiments that were related to what I had been doing in Edinburgh. And I had come across the work of those groups when I was doing my PhD. And I thought this was very, very beautiful work that I read about. And I moved there and I learned an additional technique. So I was still doing collisions, but I was using lasers in addition to the collision to excite specific excited states in the atoms. And by having nice multiple modes to pump the atoms into different hyperfine states, you could control the orientation or the alignment of the charge cloud around that atom. And you could change that orientation before the atom collided with the ion, and then study how that influenced the cross-section for an electron to jump from the excited atom to the ion. So it was very nice fundamental work. And I still think this is among the best work that I've ever done. It was very beautiful work and very nice systems to study. So I learned a lot doing that. And that was in Berlin, and then the group moved to Freiburg. So I moved to Freiburg and became an assistant professor there. And that was when I started to develop my own independent research. But 1985, when I moved to Germany, was important for me for something else, and that was the discovery of C60. I wasn't aware of this happening at the time because I was working in a very different area, atomic collisions. But I learned about it a few years later, and it was very, very important for me because most of my career since the late 1980s has been involved with fullerenes, carbon-60. So this was a very, very important event for me. And in a way, it was probably written in the stars that I would end up working with fullerenes. So I have this very nice picture from 1967 taken at my home in Butte. And this is our little research group there, or football team. I've always been a passionate football player or soccer player. And I'm the one in charge, of course. I'm the one holding the football, which is, of course, a very nice model of the carbon-60. So I think, you know, it had to happen. I had to get involved in fullerene research. And I did, but I did by chance. And many things have happened by chance, but you know, is it luck or I don't know. But I think one of the key things is knowing when something happens that gives you a new opportunity and being able to take advantage of it and having the courage to take advantage of it. And I think that's very important as a scientist, that you can do that. So I was in Freiburg, and the big boss, the professor of the group, was Professor Hertel. And just when I got my associate professor position, assistant professor position, and started to think about what my research would be to distinguish me from the big professor, he came to me one day and he said, "Wir müssen endlich mal was Nützliches tun, Frau Campbell." And that translated to English means we have to finally do something useful, right? We're doing this very nice fundamental atomic collisions, but they're of no use to anyone, right? We need more money in the group, so we need to do something useful. So I went away to the library and spent a few days looking through journals. And I came up with the idea to study ultraviolet pulsed laser ablation of materials. And we could do that because we had lasers. We had a whole variety of pulsed nanosecond lasers. And we had mass spectrometers, home-built mass spectrometers. So in the literature, I found that people, and in particular IBM, were interested in using lasers to write structures in polyimide. So this was back in the 80s, 88. So they were doing that, and they were trying to determine what laser parameters would give them the best holes or the best structures, the best defined structures. But they had a problem, and they had a problem that there was a lot of carbon being deposited on the surface. So they were looking for ways to avoid that carbon being deposited. But nobody was looking at what came out. They were just looking at what was left after the laser had been used. So I thought, well, why don't we just do that inside the mass spectrometer and look at the material that's coming out? Now, that's done a lot now, studying ablation of different materials, but nobody was doing it then. So I was in the right place at the right time to think about doing that, which again was a very nice, positive thing. So we started looking at the mass spectra of what comes out when you do this in the mass spectrometer, and lots of hydrocarbon ions, and we could get lots of nice information about the velocities of the material and how that depended on the laser power and the angular distributions and how you could get that narrower so you didn't have so much deposition. But then the really interesting thing happened when my PhD student set the oscilloscope wrongly when he was collecting the mass spectra one day. So instead of measuring up to about 300 mass units, which is about here where the signal kind of disappears, he set it to 4,000 mass units. And what happened was the signal dies away around 400, and then it comes back again. And we had these very strong peaks in the mass spectrum, all separated by 24 mass units, which is the same as 2 carbon atoms. And this is carbon-60. And from the isotope distribution here, you could tell that this was pure carbon. There was no hydrogen attached, no nitrogen attached. It was pure carbon fullerenes coming out of this messy experiment where we just had a powerful laser and we just blasted apart a piece of plastic with carbon, hydrogen, oxygen, nitrogen in it. And these molecules formed. And I was hooked. That was me, right? So then I quickly learned about the C60 discovery, which had been a few years before. And there was so much material coming out of this that I could mass select this particular mass for C60 and then study how this behaved when I excited it, how it fragmented. And that was another proof that it was the closed cage structure, the fullerenes, because they always fragment by losing 2 carbon atoms, never 1 carbon atom. And that's the most stable way, the most energetically favorable way of it fragmenting. So we could show that we had these, and we were making very large ones. So this keeps going up to 300 carbons, 400 carbons. And then the signal dies away, not because we're not making the big ones, but because we can't detect them anymore. So this was a very, very intense source. So we got that published. And then because we could mass select and study this, we looked into this, and I did something possibly foolish here. So we did a whole series of studies looking at the fragmentation, and I was convinced that this was proving that we had the carbon cages. But at this time, late 1980s, early 1990, people were beginning to doubt that Kroto and Smalley had made the soccer ball carbon-60. They were saying there's no evidence that this is a ball. It could be something completely different. And there were a few very powerful groups in the United States that did not like the fullerene description. And I wrote a paper saying, oh, this is showing, this has to be fullerenes. And I made an enemy of a very, very big American professor. And he gave me a very hard time. But on the other hand, I made a very good friend of Harry Kroto and Rick Smalley. And that turned out to be more important in the long run. So Harry Kroto read this paper, and then he came to visit me because he was so delighted that we were backing up his original suggestion of the fullerenes. So this was nice. And the other very nice thing was that this came at the right time, just before Kretschmer and Huffman published the paper that showed you could mass produce carbon-60. This was a famous Nature paper where they made fullerenes by making an arc discharge with graphite rods and collecting the soot. And this is what turns carbon-60 into a kind of unusual cluster peak in a mass spectrum into a new nanomaterial. And it really triggered the whole explosion in nanoscience that then took place in the 1990s. So this was a very important paper. And it was just after the time we had started working on C60. So perfect. Wolfgang Kretschmer just worked up the road from Freiburg in Heidelberg. So he sent me his soot before the paper was published. And I was able to play with that and to actually use the carbon-60 soot to do my gas phase experiments. So very nice situation, very nice timing, and lots of kind of coincidences coming together, but also, you know, just being able to pick up on that, and instead of saying, oh, you've done something wrong here, Georg, my student, you know, go back and fix it, to notice that there was something very interesting happening here, and to, you know, look into that a bit more. So this completely changed my whole plan of research and what I was going to do. So we studied different things here with the Kretschmer soot. Here we looked at how larger fullerenes could grow by eating up carbon dimers. And we also did a nice experiment here. So another good thing is to look for interesting collaborators. Look around you and see who there is that's doing something that would be nicely complementary to what you're doing, and bring that together to do something different and something new. And there was an organic chemistry professor in Freiburg called Horst Prinzbach, and he synthesized carbon cage molecules and first principles, you know, the real organic chemistry way, 25 steps to make a carbon-20 cage. But the pure carbon cages are not stable. So he always had to have hydrogens or halogens attached to the cage to stabilize these. But he was actually quite upset when I gave a talk in Freiburg about our fullerene experiments, where I could make the whole family of fullerenes by just shining a laser on a piece of plastic. And he was really upset about that, because he had spent 20 years developing his synthesis techniques to make these molecules. But he eventually came round. So a couple of years later, I met him and we talked about doing some experiments with his hydrogenated and halogenated cages. And this also led to a very interesting result about how these molecules behave. So here we were laser desorbing the molecules, desorbing and ionizing them with a relatively weak laser pulse. And as you turn up the laser fluence, you get more and more molecules desorbing from the surface. And when the density is high enough, these can aggregate to make clusters. So here you see the monomer species. You tend to lose the halogens during the desorption as they ionize, but you can form here a dimer with some hydrogens around. As soon as you see the trimer species appearing in the mass spectra, you also see the bare C60. And this is showing something very nice. As soon as you have 60 carbon atoms in close proximity, those carbon atoms want to form the very stable C60 icosahedral cage. Tickle them a little bit with the laser to give them some excitation energy, and they will form a fullerene. You can form fullerenes from anything with carbon if you bring the 60 carbon atoms together and give them a little bit of energy. And this opens up very interesting questions about how these fullerenes are forming in different environments, and in particular nowadays in space. So I'll come back to that later on. Okay. But these experiments that we were doing, early days of fullerene research, got us noticed a little bit. So I could go to conferences and meet all the other people building up this research field. The other nice thing was, here's a very proud day for me here. This was the graduation day of my first PhD student. This is the one who didn't know how to set his oscilloscope properly and who started all the fullerene research. This is Georg. So that's a very nice occasion here. Actually, Georg was actually younger than me, although I was his PhD supervisor. And that was an interesting consequence of the different education systems in the UK and in Germany. In the UK, we're finished very quickly with PhDs, which means we maybe don't, well, we certainly don't know as much as the German students who took another 5 years to get their PhDs, but we can start our own stuff much earlier. So it was actually quite strange for me going to Germany and having my own students who were older than me. Even the master's students were older than me. It was very strange, but I managed. I fought my way through. I showed them who was boss. And they started to listen to me after a little while, do what I said, most of them. And then in the mid-90s, I was appointed to the Max Born Institute in Germany. And this was a big step up. So I moved there to take over quite a big group. So I had a group of about 25 people. Some of them were students that came from Freiburg with me, about half of them, and about half were East German scientists who had worked in the old DDR. So that was a very interesting learning experience to bring these two groups together, get them to work together. So the older East German scientists were very, very good scientists. They were very good spectroscopists and laser people. They understood how to build lasers. They had had to smuggle lasers in from West Germany when the two countries were separated, take these lasers apart, and then learn how to build copies of them. So they knew exactly how the lasers worked. They knew exactly how to get the best pulses and profiles from the lasers. And they were very, very skilled spectroscopists. So I learned a lot from these people, although I was supposed to be their boss. They taught me a lot. And it also allowed me, again, to do new things and to do different things using the skills that they had and learning from that. And then also they were able to learn from the young Freiburg students and from me, you know, how to do new things, to have the courage to look outside their little box and try to do new things. And I remember in the early years there having long discussions with them, and I would want to try something different, do something new. And I remember the most senior one, he would sit in my office and he would say, Frau Campbell, that all sounds very interesting, but nobody is doing that. And I would say, yes, that's the whole point. Why don't we do it? Wow. And then eventually we would, and they would be very happy. But it was quite difficult bringing the cultures together and doing these things. But something I enjoyed doing and gained a lot from. Okay. This was another thing that gave me a big boost and made me more internationally visible, which is also important, right? You want the community in your own country to get to know you and know what you're doing, but you also want colleagues in other countries to know the work you're doing and learn about it. So this was early 1990. This was just about the time I had moved to Berlin and was setting up in Berlin. And there was a nice little conference on fullerenes taking place in Crete. And I got together one day with these two characters. These are both theoretical chemists based in the UK, now very distinguished professors, not so distinguished in those days. So we were all very young and keen and starting up. And this was the time when the European Union was starting to give money for European network collaborations. And I had learned about that a few weeks before from someone who visited the Institute. So I got together with Patrick and David and I said, we really need to have to try and get a network set up. First, early rounds of funding. And they were not very keen and, oh, that's going to be a lot of work. Oh, we'll never get it. Oh, no. But I said, well, look, if I tried, will you join it? Yes, if you do it, we'll join. Typical guys, get the women to do the work. So that was fine. And then at the same conference, there were the senior people. So Harry Kroto and Wolfgang Kretschmer, I've mentioned before. And then Sidney Leach, who was a very distinguished spectroscopist. So they were all there. We ganged up on them at a coffee break. And I said, we're going to put together a European application. We need you to join us. We need you senior people. I said, all right, yeah, that's never going to work. Oh, okay, let's humor her. You know, very nice people. They didn't want to put me down. So they said, all right, yeah, if you write this, we'll join in. Okay, so we got it funded. And then just a couple of years after it was funded, Harry got the Nobel Prize. So all of a sudden, the European Union administrators were very pleased with me that I had actually got a network with a Nobel laureate. So they made a big splash about that. But this gave us a lot of opportunity to collaborate with people doing slightly different things. And again, do different things, do new things. And it was a great time because we had a lot of money to exchange students. And that was when I really learned how important it is to be able to send students to other groups and allow them to experience different environments, do different experiments, and how that could lead to nice new collaborations. So I've always tried to do that ever since and give the students the opportunity to do that. And I know that works very well here in Korea. You quite often have these opportunities to go elsewhere. So what were we doing in Berlin? Berlin was a laser institute, so I had to work with lasers. And it was ultra short pulsed lasers. So again, I had something new. And I was in an institute where most of the people in the institute were developing those lasers. So I'm not a laser person. I don't know how to build a laser. But I was there when these lasers were being developed by people who knew how to do it. And they were in the next door lab. So I could very easily take my experiments and put them with the femtosecond lasers. So that gave me a big jump ahead in looking at what happens when you excite these big molecules with ultra short laser pulses. So another nice aspect. So we did a lot looking at how, you know, isolated fullerenes behave when you excite them in different ways, and looking at fragmentation processes, looking at black body radiation from the excited molecules, thermionic electron emission, lots of different processes that can cool the molecules down. And these studies now, although they were done quite a long while ago, they've actually become very relevant again and relevant for astrochemistry. So a different field. I have never been an astrochemist. But these old studies that we did are now relevant for understanding how carbon-60 can survive in space and what its role is in carbon chemistry and charge distributions in space. And again, I'll touch on the C60 in space right at the end. I need to watch my time here. I also went back to laser ablation, right? That's what started off my fullerene story. And here, because we had nice ultra short pulsed lasers in the institute in Berlin, I thought, well, nobody was actually looking at what happens if you laser ablate with those very short pulses. It was just beginning to happen in a couple of labs. And it turns out that if you use ultra short pulses for dielectric materials like quartz, you can get very nice, well-defined structures, which you can't make with nanosecond lasers, because nanosecond lasers heat it up too much and you cause damage to the material. But if you use short pulses, you can very, very cleanly ablate it. So we were able to study this, and we were able to look quite a lot into the mechanisms that were leading to this nice behavior. And in fact, show that you don't want the very shortest pulses, so it doesn't get better and better as you go to shorter and shorter pulses. What you want is something in the picosecond range, because that really optimizes, it limits the damage that you get from the high pressure effects with femtosecond pulses, and it limits the heating that you get with the longer nanosecond pulses. And that was and I just did that because I thought, well, look, our laser people know how to tune the duration of their pulse. Why don't we look and see what happens at picoseconds and not just of everything femtoseconds? The laser people wanted nothing to do with that. They want to use the shortest pulses that you can possibly have. But I was saying, but no, maybe it works differently with picosecond pulses, and it does. And actually, the papers we published then, we didn't publish them in, you know, high impact journal. We published them in journals like Applied Physics A, which you've probably never heard of. It has an impact factor of 1.5 or something. These are my most cited papers. Well, actually, it's the PRB one that's the most cited, but quite a lot of my Applied Physics A ones are very highly cited. So this will probably be my most impactful work, although it's not something that I was particularly proud of at the time. So you never know. You never really know what your work is going to lead to in the long run. Okay. I was still able to do collision experiments, which were my first love. This is my favorite collision experiment. This is my least cited work, but it's very nice. And I was really proud of this apparatus. The nice thing working in Germany was you had very good workshops, and it was very easy and inexpensive to build equipment. So I loved designing apparatus, and I was very good at it and getting it built in the workshop. And this is one that was called SOCCER, which is scattering of carbon clusters energy resolved. So here we studied what happens when you collide C60 ions with C60 neutral molecules. And if you choose the collision energy right, you can fuse these together and they form a larger C120 cluster. And we can tell that's what's happening from the fragmentation pattern of the product and from the angular distribution of the products. And what I really liked about this was that you could take models from nuclear physics, nuclear collisions, and those models actually can reproduce very nicely the dynamics that you get in these C60 collisions. So I had a lot of fun for a few years going to nuclear physics conferences and talking about carbon-60 collisions. Very important in this was, again, finding the right collaborators. I'm not a theoretician, but I thought it would be very nice to be able to model these collisions. So we had a nice collaboration with people in Dresden who were doing quantum molecular dynamics simulations. And we were able to model the experimental results very nicely with these molecular dynamic simulations. And the other thing I did here that again got me noticed in the community, when you're giving a talk at a conference or a workshop, sometimes it's nice to do something a little bit different that gets people's attention. Then they'll remember you, as long as they remember you for the right reasons and not the wrong reasons, right? The thing I did here was I convinced my theoretical collaborators that we should make videos of these molecular dynamics simulations. Nobody was showing videos of molecular dynamics simulations at the time. You couldn't just, put it on your computer and have it run on the screen. You needed to make the movie and put it on an old VHS cassette and then make sure that the conference people had a video player that you could use. So it was very complicated. But I suggested this to Rüdiger Schmidt, and he was an old school nuclear physicist from training. And he said, "What, you want to make a movie? Nonsense, nonsense. All the information is in my boring black plots." I said, "Yeah, that may be, but if I put boring black plots up in my presentation, nobody's going to pay any attention." So he wouldn't do it. But we had, my PhD student was running the calculations in collaboration with them. So I just said to him, "Look, take those coordinates and you make the movie." So he did, and we showed the movie of these colliding fullerenes at a couple of conferences, and people loved it, and they remembered it, and to this day they remember that I showed those movies in my talks. So it's very nice if you can think of doing something, doing a simple little demonstration that illustrates what you're talking about. People will remember that, and they'll remember you for it. Okay. And these are the other collisions that I love. So this was putting ions inside the carbon-60 cage. And these are the experiments that the fullerene community knew me for. Because this was a very nice way to make endohedral fullerenes, where you could change the properties of the cage by putting something inside. So we made lithium. We could even put 2 lithiums inside. And we could, to a certain extent, study the properties of that. But we weren't clever enough to be able to mass produce it and purify it and have it as a useful material. But actually a Japanese group in Sendai took this up and they used this ion implantation technique to make this molecule. And now there's a company that sells it. It's probably the most expensive material in the world because you only get tiny amounts for a very large amount of money. But this actually does have very, very interesting properties. It has interesting electron acceptor properties. So people are looking at this for a component of organic solar cell materials and various other things, interesting biological aspects. And we've come back now and are now looking at this with scanning tunneling microscopy and seeing some interesting things that I'll show. So yeah, lots of stuff going on. Then I moved to Sweden, to Gothenburg. And here, what was nice about the university in Sweden was that there was a very, very fancy nanofabrication clean room. And I didn't go there because I wanted to do nanofabrication. I went there to continue my fullerene work and so on. But once I was there, I thought, this is such a fantastic facility. I have to think of a way of using it. And carbon nanotubes were becoming very popular there as a kind of side shoot from fullerenes. And one of the postdocs that I appointed, he had been a PhD student with me doing the fullerene collisions. Then he worked with Smalley in the States, and I wanted him to come back and work in my group in Gothenburg. So he said to me, well, I really don't want to do these fullerene collisions. They're just so difficult and it takes forever to get a paper. I don't want to do that anymore, but I do want to grow carbon nanotubes. So I thought, all right, fine, come and we'll grow carbon nanotubes. So that's how I started with carbon nanotubes. And he was only there for 2 years, and then he got a job with Zeiss in Germany, and he's now the director, big director at Zeiss and a big boss there. But he was a very, very clever guy. And he started our nanotube activities. And that became the main focus when I was in Sweden. And these are some of the things we did. So we did a lot of growth and thermionic emission stuff, electron emission, tunable photonic crystals, NEMS, nano electromechanical systems. And this was a lot of fun. And again, I was learning completely different things, how to do the fabrication. I had to learn some electrical engineering where we're doing radio frequency measurements. How do you make the structures there? How do you analyze what's happening? And this was when my interaction with Korea started around about 2001, 2002. I came to Korea for the first time in 2002. And I met Professor Young-Woo Park at Seoul National University. And that brought Professor Lee to my group, which was very nice. So Professor Sang-Mook Lee, whom I'm sure you know, was a PhD student with Professor Park. And Professor Park wanted to send him out to another group, and he sent him to me. And it turned out that Sang-Wook was a wizard at doing nanofabrication. He would live in the clean room. I don't think he ever came out of the clean room. And he came up with lots of ideas to make little structures, and he was able to make suspended nanotube devices, and we did lots of beautiful work there. A nice combination with the growth studies. So Roluka was a PhD student growing the nanotubes. Sang-Wook was making the devices. So that was a really nice time. We had other Korean students coming to visit, and that was very important. And having good students makes an enormous difference. And these Korean students who came to my group in Gothenburg were fantastic, worked very hard, showed the Swedish students how to work, which was very important and very useful, because it meant the Swedish students had to up their game and work as hard as the Korean students. And it was a really great time. Then I got the chance to come back to Edinburgh, and we continued nanotube work. We did other things, and mainly I went back to the C60 and did photoelectron spectroscopy with fullerenes. And I'll say a little bit, a few minutes about the work I'm interested in now, the research I'm working at now. But I wanted to point out that with increasing success, and I had a lot of success, I was very lucky with the things I tried that worked, and some of them were a bit crazy, but they paid off. And I had a lot of fun learning new techniques, bringing things together, working with different people. But as you get older and more distinguished, and I never think of myself as distinguished, but you know, other things have to be done. So you get asked more and more to be on committees, particularly if you're a woman, because there are very few senior women. And as soon as I moved back to Edinburgh, this really hit me. Before I moved to Edinburgh, I always felt I was one of the junior people in the department. When I moved to Edinburgh, all of a sudden, I was one of the most senior people. And I had to do all these kind of things. So being asked to be in committees, reviewing other people's research, being on committees that fund other people's research, being involved in refurbishing buildings. I did a lot of that in Sweden. I continued to do it in Edinburgh. Getting more involved in teaching development. And this is something I wanted to do in Edinburgh because I wanted to take the chemical physics degree and bring it up to date, make it more exciting for the students. And then getting elected to academies, right? I mean, a whole list was read out at the beginning. Being elected to the Royal Swedish Academy of Sciences was wonderful, right? Because these are the people who hand out Nobel Prizes, right? And this was fantastic to be involved with that and to see how that happens. That's very, very interesting. And this is one of the Nobel ceremonies. I'm sitting in the back row in this one here somewhere. So getting to go to these fantastic ceremonies every year and being involved with that was really nice. In the UK, being put in positions of responsibility, heading departments, heading the School of Chemistry, huge amount of administrative work. So you get pulled away from the research. Right? And in a way, this is fine. I think that's what should happen as people get more and more senior. You know, you should step back. You should let the younger people take over and give them the resources to do their research. And that's what I'm doing now. So my labs are being handed over to the younger people. And I'm doing more of this kind of work and less of the actual hands-on research activities. And it was quite a difficult step to take because research is so much fun and it's so much part of you as a professor, right? That's what you go into academia to do research. That's what excites you. So when you feel yourself drifting away from the research, it can be quite challenging. But as soon as you recognize, but yeah, that's right, that's how it should be. Right? I can use my experience to help the younger people and to think more about how science should be done and how it should be funded. And so now I'm quite happy about this, but I still have to have some research going. And I still love to learn about your research and look at what you're doing. And that gets me interested and keeps me going. So that's where I am. And this is what I'm doing now. So it's all related to the photoelectron spectroscopy on the fullerenes that we started a few years ago. And in particular, looking at these very special excited states in the molecule. So this is very fundamental spectroscopy work again here. And these are known as SAMO states, superatom molecular orbitals. They're very, very diffuse, low-lying Rydberg states in the molecule. And they look just like very large hydrogen atom wave functions, molecular or orbitals, right? There's the S1, the P, the D. And they're very special because these orbitals are all centered on the center of this hollow carbon cage. And they have very nice properties. And the way we look at these is with a very strange technique, and it always amuses me, or I wonder why it works so nicely. Now I know why it works so nicely with the fullerenes, but for a long while I didn't know. And you take a short laser pulse, femtosecond pulses, and you excite with multi-photons up to the Rydberg range. So you have a lot of closely spaced Rydberg states. You populate many of these, and then in the same short laser pulse, you can remove these Rydberg electrons because you've got a very high probability of ionizing from these states. And those electrons coming from these very diffuse low-lying Rydberg states have these beautiful structures, and you can determine the angular distributions by looking at the angular distributions in the photoelectron spectrum. And you can work out what orbitals these electrons are coming from. And in the photoelectron spectrum, you have this very large, complex molecule with many degrees of freedom, but you get a very simple, very clear photoelectron spectrum. If you do this with a normal big molecule with 60 carbon atoms, you don't see anything like that. It's all smeared out. And these are signals that come from these beautiful diffuse SAMO orbitals. So I was very interested in those. But then I asked myself, well, what happens if you put something inside the cage, right, and destroy the symmetry? So this takes me back to my lithium C60 that I made many years ago by pushing lithium ions into the cage. And if you do it with lithium C60, if you measure the photoelectron kinetic energy, it looks quite similar to the empty C60. But because the ionization energies are different, if you look at the SAMO excitation energy, it looks very different. Right? They get spread out, and these excitation energies of these states are moved to much lower levels. And if you look at what these molecular orbitals look like, if you trust theoreticians to calculate it for you, they look very different. So the lithium inside the cage distorts these nice diffuse orbitals. So we studied this, and we could tell, you know, that again, we had S, we could split up the P's because the symmetry is broken. So we have a PZ orbital, PXZ orbitals, and we can look at the angular distributions and compare with theory. That's all very nice. Now, but these experiments were quite tricky because when we heat up the lithium C60, we can remove the lithium from the cage. And to interpret the results here, we needed to know how much lithium C60 we had and how much empty C60. And because this molecule is rather unstable, mass spectrometry wasn't helping us, so we couldn't work it out. So what we had to do was find somebody with a nice scanning tunneling microscope, because I thought here, well, what we can do is we can use the same conditions to evaporate our molecules, deposit them on a surface and image with STM, and we should be able to tell the difference between the C60 and the lithium C60 from the STM image. So it so happens that our partner research institute in St. Andrews, we formed the East Chem research collaboration, has a beautiful ultra high vacuum, low temperature scanning tunneling microscope. So that was the next technique that I wanted to learn. And this is a beautiful technique, and you can learn so much about this and do so many things. So here you can look at the difference between what you learn with the gas phase and what you learn with the STM. Here you're looking at isolated molecules. You can directly probe the orbital symmetry and compare with high-level calculations. But there are issues with the high temperature that you have in your beam and also losing the lithium from the cage. With the STM, you can use low molecular temperatures, freeze it down to 6 Kelvin. A nice advantage is you can image both the occupied states in the molecule and the unoccupied states by changing the bias of your STM tip. So you can learn a lot about the electronic structure. You can also get spectral information from doing scanning tunneling spectroscopy, but you have the interaction with the substrate, which can complicate things. But anyway, here we can, so here we have a mixture of C60 and lithium C60. And lots of people have studied C60 with scanning tunneling microscope. And if you have high resolution, you can tell exactly the orientation of the C60 cage on the surface, because you get a different image depending on whether a hexagon is sitting at the top or a pentagon or a carbon-carbon bond. So you know how the molecule sits on the surface. So these different structures are all carbon-60, but sitting on the surface in a different orientation. And now as you scan, so this is looking at occupied states with a negative bias. And as you scan through the bias in our mixture of C60 and lithium C60, the image changes because you're imaging different occupied states. Then you can change to look at the unoccupied states. And then when you get to a certain bias voltage, some of these fullerenes light up. You can see the lighter little light bulbs shining out here. These are the lithium C60. And what we're imaging there is the S-SAMO of the lithium C60, which really shines up at that particular bias. So that's how we can tell how many lithium C60 and how many C60 we have. We just count the light bulbs at that particular bias voltage. So the little S-SAMO lights up. And this is how it sits on the surface. So lithium sits at the top of the cage. This diffuse lobe is at the opposite side of the cage, and that interacts very strongly with the gold surface that it's sitting on. So you get a very high tunneling current when you're resonant with that state. And it always sits hexagon down. It's very, very stable because of the strong interaction that the cage has with the gold, with the charge transfer from the lithium inside the cage. Now what we could do here is then, well, let's play with this. So we have a lithium C60 there. We know the lithium is sitting at the top of the cage. What happens if we apply a strong current to that molecule? So we sit with our STM tip over one of the little light bulbs, and we apply a pretty powerful pulse to that, 5 volts and 2 microamps. That's a lot of current for a single molecule, right? Normally you would just destroy molecules by doing that. Oh, maybe we did destroy the molecule because we lose the light bulb, but we apply the pulse again and it comes back. So we can switch this on and off, and we can do that many, 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 many times. So what's happening? Well, what we're doing is, and here we can also see different positions. So if you look carefully here, you can see very subtle changes in the image, and those are showing us different positions of the lithium inside the cage. The brightest signal is when the lithium sits at the top, the most energetically stable one. But then when we apply our pulse, what happens is we excite the lithium inside the cage and it moves, it rattles around. Right? So it's like a little maracas, right? Give it a shake and it moves around. And then the energy will distribute into the substrate, it cools down and it stops against a hexagon. And it stays against that other hexagon. So there are actually, we can distinguish 14 different positions of the lithium inside the cage. So against the lithium at the top and the bottom half, and then next to bonds around the center region of the cage. And that's due to interactions with neighboring molecules. 14 different positions. And more importantly, we have 5 distinct tunneling currents. So we have a very nice single molecule switch where we have 5 different current levels that distinguish the switch positions. And we can tell by studying when it switches, when it doesn't switch. We need a voltage of about 5 volts, 4 and 5 volts, in order to switch, independent of the current. So that voltage is very important. And it appears that what's critical is getting a resonant excitation of the pxy SAMO orbital. And that's very important for the switching mechanism. So how is that happening? Now, there are typical ways you have single molecule switches. You can have an electric field effect, but that's strongly dependent on the bias voltage, but you can reverse it when you reverse the bias. We only switch for one bias, and it has to be positive. So it's not an electric field effect. You can have inelastic electron tunneling. This has much lower bias voltages to get the inelastic tunneling. our energy barriers for switching are very low, so much lower than the 3 to 5 volts that we need to get this switching. You can do that for other endohedral fullerenes, but that's not what's happening for lithium C60. So the resonant tunneling through the SAMO is really the only mechanism that seems to fit. So we have resonantly excite the PXY. Why the PXY? Well, we're seeing that from the voltage that's needed. This is also the SAMO that penetrates most into the cage and where you can have an interaction with the lithium ion. And it's also the one that has the least interaction with the metal substrate. So the S and the PZ orbital couples very strongly to the metal, so it doesn't affect the lithium. The energy just goes directly into the substrate. PXZ, you have the chance to couple that energy to the lithium motion and give it that shake that it needs, and then it settles down in the new position. So that gives us hope that we can actually maybe use light to induce the switching, and that's what we're working on now. We're coupling a laser into the STM, and we're going to try to see, we think we've seen some evidence for it, but not enough to show you. We're going to see if we can try and use that optical resonant excitation to have the same effect. And then perhaps we can find a way of directing the position that the lithium goes in and having much more control over our 5 current levels in our switch. So that's what we're looking at and trying to develop that. But we're also learning all sorts of other very interesting things that we don't understand about how these molecules talk to one another on the substrate. We can switch a lithium C60 in one position, and then it affects another lithium C60 a long distance away if we do it in a certain way. So there's a very strong interaction between the molecules on the substrate, which is very interesting and something that we're trying to understand. Okay, so that keeps me interested. With all my committee work, I can come back and I can get excited again about the STM and what's happening there. Okay, so I've had a long journey, and a long talk, I better stop, throughout Europe and elsewhere with lots of collaborations. It's been a great way to pick up new techniques, broaden a network, find lots of different people to collaborate with the skills and the expertise that I need. And that's been very important for all the things that I've been able to do. So what would I advise you? I would advise you be passionate about your science if you're going to go into research. You need that passion to really drive it and give you the power to make good progress. Always look out for possibilities to collaborate and learn about new techniques. Broaden your network, use conferences, talk to people, and don't be afraid to write to people about your research or about their research if you find it interesting. Let them know that you find it interesting. Perhaps that's someone you could do a postdoc with, or someone who could be a good referee for you when you're looking for a position. Think about that very early on. Huh? We talk about cultivating your referees. Very important. Don't be afraid to cross disciplines and do crazy, difficult things. You just have to hope that they work. Sometimes they'll work, sometimes they won't work. I haven't told you about the ones that didn't work. But just be careful that you always have something where you're sure you can get some results so that you can keep publications coming up. Offer to help organize conferences. That's a very good way to meet influential people. Always question what you and others are doing. Is this the right thing? Is this really correct, what they write in that paper? But most importantly, be nice to people and have fun. That's the most important thing I can say to you. Okay, I'm going to stop here. This was a bit of fun, but I don't have time. I'll just point you in this direction to this YouTube video. This was a lockdown project where we took the C60 plus spectrum that my young colleague Ewan Campbell measured in the lab. And this was the proof that C60 plus is present in large amounts in the interstellar medium. And it has 5 very nice, clear transitions. And my colleague, who's a medical chemist, Colin Campbell, is also a very keen musician. And he was looking for something to do during lockdown, and he had the idea to take experimental results and turn them into a piece of music. So I said the obvious thing to do is to take Ewan Spectrum. So he did. And then we thought of a nice video to go along with it. And I actually have a little project at the moment with astrobiologists where we're looking at whether C60 could have been important as a feedstock for the early stages of life. So we come up with this little idea for a video and had an art student to make the video. And if you're interested in the results, you can go and look at it here on YouTube. That was great fun to do too. Okay, so thank you very much for that. I hope I could give you some advice. I hope you found my story interesting. And I just want to say a thank you. And for those of you who like animal pictures, these are my two best friends, Fudge and Ginty, that keep me happy when I'm not in the lab. Okay, thank you.